This brief tutorial will show how easy it is to obtain buckling factors and modes in SAP 2000. The buckling factor determines the magnitude of the load required to cause buckling of the structure. For this tutorial, we have created a simplified one-circuit transmission tower. Transmission towers are often susceptible to buckling due to the slenderness of the members used in their construction. For this model, we have defined three load patterns: the dead load, which includes the self-weight of the tower; the wire load, that is, the load from the wire spanning between towers; and the wind load. The key to obtaining the buckling factors and modes is the creation of a buckling load case. However, before we create a buckling load case, we will create a P-delta load case. This is important as P-delta alters the stiffness of the structure and thus affects the determination of the buckling modes. P-delta is a nonlinear analysis, and for this we will use the P-delta plus large displacements option, although P-delta by itself is typically sufficient for most structures. For the applied loads, in this P-delta analysis we will use a combination of 1 times dead plus 1 times the wire load. Next, we will define a buckling load case. Here, we use a load case type of buckling. In the stiffness to use area, we are going to select the stiffness at the end of a nonlinear case, and we will use the P-delta load case just defined. This means that P-delta will modify the stiffness matrix used in the buckling analysis. For the applied loads in our initial analysis, we will use the same loads as used for the P-delta, namely 1 times the dead plus 1 times the wire. These loads multiplied by the buckling factor and added to the P-delta loads give the buckling load. We will leave the number of buckling modes set to 6 and the convergence tolerance as is. Calculating the buckling modes is an iterative process, and the tolerance determines how numerically close the iterations need to be to assume that convergence of the buckling factors has occurred. We can now run the analysis to include the buckling load case. With the analysis complete, we can display the buckling modes and factors. This can be done through the display Show Deform Shape command. Selecting buckling for our case, and then Mode 1, the first mode of buckling and the accompanying buckling factor are displayed. Note that the first mode of buckling will occur if we increase our applied loads by a factor of 3.828. Remember this number, as we will come back to it shortly. Using the VCR buttons, we can step through the other 5 buckling modes. We can also display the relative forces in the members for each buckling mode. Selecting the first buckling mode and the axial force component, we see the deformations in the first buckling mode are primarily isolated at the bottom of the tower. As we go to the higher modes, we see that different regions of the tower are involved in the buckling. Lastly, buckling factors may be displayed using the Display Show Tables command. The factors for the 6 buckling modes are displayed. Next, we will unlock the model. We are now going to add a copy of the buckling load case to include wind in the applied loads to see how that affects the buckling factors and modes. Selecting the buckling case and clicking the Copy Case button. After naming our case Buckling Wind, we add the wind load pattern to the loads applied list. This is the only change we will make. After rerunning the analysis, we can redisplay the buckling modes to see how adding wind to the buckling loads affected the results. On the left, we will display the buckling modes with wind, and on the right, the original buckling modes without wind. Note that the buckling factor for the first mode has dropped to 2.493 as expected due to the increase in load applied. As we go up in modes, we can see that the shape of the modes is also different. It is important to note that the applied loads influence the determination of the buckling modes. This concludes this tutorial on buckling.